Welcome back, everyone. To finish off this section, we'll show you how to generate predictions using our trained model. Let's get started. Okay, here we are back at our notebook. What we need to do now is create two functions, one that will predict at a character level. So given a model and given a character, it'll go ahead and predict one character out. And then another function that will basically use that helper function to repeat it to generate as much new text as we want character by character. Let's go ahead and create a function called def, and it'll be predict next character. I'll go ahead and zoom in here. And then this function will take in the model, the character, we'll say hidden starts off as none, and then we'll set k is equal to 1. K is something we're going to use later on to return the k largest probabilities in a tensor. So first off, what we're going to do is we're going to encode raw letters with the model. So basically, inside of this function, we create some encoded text, which is the model. We call the encoder off of that model, and then we pass in the single character in order to encode it to the same number that the model expected. Now what we need to do is we need to turn this into a NumPy array. So we'll say encoded text is equal to, in order to make sure it has the correct dimensions, we're going to pass in as a single item inside of another array the encoded text currently. So notice these double sets of brackets. So we have this character, it's been encoded, so now we have this number. We convert this to a NumPy array, and then we're going to one-hot encode it. So we'll say, again, encoded text is equal to the output of one-hot encoder, pass in that encoded text, and we're going to say model.allCharacters, because recall that the one-hot encoder, if we take a look at it, it expects the number of unique characters, which should be the length of all the characters that that model saw. Next, what we're going to do is convert that to a tensor. So we'll say inputs is equal to torch dot from NumPy. Go ahead and grab encoded text. We'll check if we were using GPU. So we'll say if model was using GPU, go ahead and say inputs is equal to inputs.CUDA. After that, we want to grab the hidden state, so we'll say hidden. And we'll use the same code as we did before, basically saying state data for state in hidden. And later on, we'll see what we actually pass into hidden when we're calling the predict next character function. Then we're going to want to run our model, so we'll say lstm out. We also get the hidden output is equal to model inputs and hidden. And then we're going to convert LSTM out to probabilities. So these actual probabilities is then passing this through a softmax activation function. We'll say LSTM out along dimensions equal to 1. And here we just want to grab that data. This essentially gives us the raw probabilities for every single character. And now, in order to use this with NumPy to pick the letter with the probability that we want, we'll go ahead and say if the model was using GPU, go ahead and take those probabilities and move them back to the CPU. And this is so we can use it with NumPy. So now we have probabilities, and what we're going to do is we're going to say probabilities, go ahead and return top k. So k basically returns or determines how many characters to consider in our probability choice. So you can check out our lecture notebook. We link to this actual method so you can check it out. But essentially, the idea here is that every single character, the model is going to predict the next probability subsequently for every single character. So maybe the character A has a 50% probability, character B has a 40% probability, and then every other character has somewhere adding up to 10%. So what we want to do is basically randomly pick characters with the probability distribution that the model thinks. So what we'll do here is we'll say probs, comma, index underscore positions is equal to probs.topk, passing in k there. Next, what we'll do here is we'll say index underscore positions, and then we'll say index positions dot numpy. That's why we had to put it back to the CPU, and then say dot squeeze to get it into the right shape. Then we create an array of the probabilities. So we'll say probabilities is equal to probabilities numpy. Flatten that out. Convert the probabilities per index. So we'll say probs is equal to probabilities divided by the total sum of all those probabilities. And now we finally choose a character based off those probabilities. So we say that the next character is equal to np dot random choice based off those index positions where p is equal to probs. And finally, we return the encoded value by saying model dot decoder of that predicted character. And we can also pass in the hidden state in case we want to keep predicting more and more characters after this. So we go ahead and run that. And next what we're going to do is create one more final function that will essentially keep calling this predict next character as many times as we want. It will also take a seed. So say def, we'll call this generate text, takes in the model, the size, essentially how many characters out do we want to predict, takes in some seed to begin with, so we can seed it with maybe the string the, and we can set something like k is equal to 1, which again has to do with the top k, so basically grab the top 1 most probable character, the top 2 most probable characters, etc. And we can later on play around with that value. Higher the k, the more likely you'll have a different character show up, but it also then leads to possibility for more misspelling since lower probability characters are now being considered. So say if the model was using GPU, go ahead and set the model on CUDA. Else, we'll say, let me get some screen here, model.cpu. Okay, so we set our model to evaluation mode. We'll set output underscore characters is equal to C for C in seed. We'll initiate that hidden state by saying hidden is equal to model dot hidden state 1. We'll predict the next character for every character in the seed. So for every character in seed, go ahead and grab the predicted character as well as the hidden state. And then we'll call predict next character, given the model, the character, whoops, make sure it's a comma, the hidden state, and then we'll say k is equal to k provided by the user. And then what we're going to do is we'll have output characters, and we'll go ahead and say append those characters. And now what we want to do is generate the size requested. So for I, in range size, what we're going to do is essentially the same code, get the prediction, so we'll say predict next character based off the model, except this time we're going to start generating predictions off predictions. So we'll go ahead and grab the very last prediction off the output characters by saying -1, pass in that hidden value or hidden state, and then say k is equal to k. And then we'll say output characters, go ahead and append the predicted character. And after that, we've predicted or generated text for maybe whatever size we requested. So then we're just going to return a string. We'll say return, and we're going to join everything in that list together. So we'll say output characters. Go ahead and run that. And now let's go ahead and call this. We'll say print. We'll say generate text. Pass in our model. Let's go ahead and predict 1,000 characters. We'll set a seed. We'll just say the space. And then we'll set k is equal to 3. So essentially, we'll be looking at the top 3 most likely choices for the next character. So we'll go ahead and run that. And it looks like we got a slight typo, index position. So let's come back up here, make sure we fix that. Positions. And make sure that matches up here. So positions, index positions, index positions. Go ahead and rerun these guys. And now let's run it. And we can see here it's running. And now we can see the Shakespeare that it's basically generating for us. So it says the princess. And while this may or may not make sense, so second lord, what is the same? First lord, why, how now? Truly I will not. You can see that this definitely feels like some Shakespeare play. And it can even understand that these sort of actions of characters entering as well as certain characters being capitalized and then their actual dialogue. And the really amazing thing here to keep in mind is that the network is doing this character by character. It's not doing this word per word, but it's actually now remembering I should have then a bunch of spaces after this line of dialogue, then something in all caps, then another line of dialogue, a bunch of spaces, all caps, etc. Then a bunch of new lines. If I want something to enter, I say enter, etc. Okay, so I hope you have now fun generating text based off of your own text datasets. Thanks, and we'll see you at the next lecture.